Ella?
This meeting is being recorded.
There we go. Okay, cool. Hello, everyone. Welcome to the Sage Live February 2023. And before we start, let me just briefly remind you what the Sage journey is all about and how Sage Live fits into that journey. So Sage Journey is a program whose mission is to inspire and encourage students to explore STEM careers for their future. We do this by offering free summer camps, paid internships, professional growth sessions, and many opportunities to connect with professionals who care about you and your future. Sage Live is part of that Sage journey. It's an online gathering of students who have attended the summer camp and are curious about next steps in their Sage journey. It is also a time to reconnect with some of the Sage volunteers. And so I know both of our speakers were volunteers in the Los Alamos camp in the past. So we have Sage Live held monthly via Zoom between the months of August and May. And the topics covered are relevant to your journey, whether it's career related or new and exciting topics such as quantum computing, AI, or space, like we have today. So today we have two speakers from Los Alamos National Lab in New Mexico, and they will share a little bit about their career path and their current research. So feel free to join the conversation by asking questions in chat, and then we'll have a chance after the talks to ask questions in person, like, by unmuting yourself. All right, so let me introduce our first speaker. Wendy Caldwell is a scientist in the Verification and Analysis Group. She also works on planetary defense and is a member of NASA's Impact Modelers Working Group on the Double Asteroid Redirection Test, or DART, mission investigation team. You might have seen that in the news a couple months ago. So excited to hear more about that. Prior to becoming a staff scientist, Wendy was a Chick Keller Postdoctoral Fellow in Space and Earth Scientists and a year-round graduate research assistant at the Lagrangian Codes group. Wendy is an expert in differential equation models and helped to develop the first, epidemiological model on prescription opioid abuse. A former college dropout, Wendy graduated with a BS in mathematics from the University of Tennessee in 2014. And then she got her master's in 2017 and PhD in 2019. In addition to her scientific endeavors, Wendy is an active member in the local performing arts community. She's on the board of directors for the Los Alamos Little Theater and the Los Alamos Light Opera. And she's the director and choreographer of Matilda, the musical, which has been playing last weekend and this weekend in Los Alamos, and previously directed Clue on Stage in 2022 and The Viewing Room in March 2022. She's performed in a number of ballets and will be choreographing upcoming May performance of Chicago. And she also has a cat, Sebastian Mouse Rat Caldwell Launcher, who, of course, for short, she calls Bash. Anyway, so that's just a little bit about Wendy. Thank you for being here today, and go ahead and take it away.
Thank you. And hopefully you'll see my cat at some point. He generally does show up when he hears voices that are new to him. So he's already shown up once today. All right, let me share the correct screen. All right, can everybody see the screen?
Yes, I can see it.
Yes, we can. Yeah.
All right, great. So I'm Wendy. I go by Wendy. Please don't call me Dr. Caldwell. Nobody does. It weirds me out. So I wanted to share my research, but also my career path. As you heard, I am a former college dropout. So, that's cool, I guess. So why I chose to study science. So I want to give you an idea of who I was in high school back in the late 90s, early 2000s. I'm president of National Honor Society and Latin Club and mock trial, be jealous. Editor of the newspaper. I was on the academic team, like trivia. I competed at the state level in U.S. history, Latin, algebra, geometry, and pre-calculus. And I won awards in Latin and pre-calculus. I am also the only female from my graduating class to get a math award. So that's pretty cool. Non-academic, I was secretary of drama club. I did a lot of children's play and musical theater, which I still do. I did peer education through skits. I was a peer leader. I was co-author and co-copy editor of a book we did on our local VFW founding members who were all World War II veterans. And the guy I interviewed was at D-Day, which is pretty cool. And I did character education every week. So that was me in high school. Academic stuff and non-academic stuff, but not a lot of science, you notice. All right, college to now. I dropped out of college in 2006-ish, I think, because I was sick and poor and ended up working multiple jobs to get my bachelor's degree. I worked 4 jobs. I had to file bankruptcy because of my medical issues and I couldn't get student loans. So I moved into my dad's basement like Batman and finished my degree. With
Are you trying to advance slides? Because we're still on the first one. Is that what you want?
I have advanced slides. I don't know why it is not showing. It's a lovely picture of me in point shoes. Is everybody else having the same issue?
Yes, yes. I think it's not
One thing I
moving.
can do is email the
yes.
slides.
It's
Here we
moving.
go.
Okay, have we caught up?
We
Yes.
are with the one of you in point shoes.
Yes.
All right, great. Well, thanks Comcast for this wonderful internet. All right. So I went to University of Tennessee undergrad. Go Vols. Our Lord and Savior Peyton Manning is on my wall right over there. He watches over me when I do work. I have a picture of him. I have an MA and a PhD in applied math from ASU because I hate precipitation. And so moving to a desert was the right call. And I love science. I love being creative. And I think that science is inherently creative. And it's something that I don't think is advertised enough. Here I am on the right in Peter Pan. That's about 4 years after my doctor said I would never dance again. So, ha! And I still dance today, to this day. I have Giselle coming up in May because I'm a crazy person who doesn't sleep, apparently. All right, I have moved forward. Do we see the new screen?
No, I think we still.
Yeah,
in the
no, we
one.
don't see it.
Okay, okay, now do you see it?
Yes.
Okay, so I need to be not full screen mode. Good to know. Okay. Before I became a scientist, I did a number of things. In the top left, you can see there's me as a 12-year-old in a music video, which was my first job. So I told my parents I wanted to be an actress. So when I was 12, they got me an agent for my birthday and were like, go be an actress. So I did, and that was fun. I worked at Chili's as a line cook. I do still eat at Chili's. Everybody I know who's ever worked there does. I worked at Blockbuster. That dates me a bit. I worked at newspapers. I was a manager at Starbucks for a while. So I had a lot of different jobs before I settled on science and math. So my daily life, my family thinks I do math. Nobody in my family does STEM, so they don't know anything about what I do. I have a lot of meetings, so that's what my kids think I do. They're not wrong. I have an ever-growing to-do list, right? I also have a to-do list where I list my accomplishments, and I highly recommend that if you're somebody like me who gets overwhelmed with the to-do list. And what I actually do is really cool science stuff. Scientists and mathematicians are people too, so I have some images to just demonstrate that. On the left, this is me with my clue cast. That was from last November. This is me in Blithe Spirit as a ghost. I play a dead person a lot on stage. I don't know what's up with that, but bottom right, that's my cast from Viewer Room. That's the first show I directed. Right here we have Matilda that's on stage now. We're closing tonight. And then me after night 2, putting gems on my face because I found that makes me feel good about myself. So, you know. And then my husband and I, we've been married 3 years this next month. And my bullet journal, I'm very into bullet journaling. I also find it's great to have creativity. And this is my theme for this year is Walt Disney. If you can dream it, you can do it. So that is a brief kind of summary of how I got to where I am. So once upon a time, I will never not share this cartoon. It's my favorite. We have some dinosaurs who find a magic lamp and they rub it and they want some meat. And then they want to be showered with meat. And then they want a meteor shower and then they panic. So probably not accurate, but we weren't there, so we don't actually know. But as you probably know, the dinosaurs are extinct, and that's because of a large impact from an asteroid. And how do we prevent ourselves from going the way of the dinosaurs is a big part of my work. Some noteworthy events in the 2010s. In Chelyabinsk, there was a meteor airburst about 20 meters across over Russia. Very pretty pictures. Knocked out some windows and stuff. On the right of Botswana, in 2018, there was a meteor airburst. It was a lot smaller. If you Google Botswana meteor, you can find a video of it. It's very cool. This is a still from the security video. So you can see it coming in and exploding in the air, and that's very cool. So there are things that come into the atmosphere every day. Small things we just don't really notice or look for because they blow up in the air, right? Impact structures on Earth. So here's one of my favorite questions to ask. And I will preface this, nobody gets this right. So the point of me asking this question isn't to get it right. It's to get you to think and to not be afraid to be wrong, because it's a whole lot about being wrong. Knowing what doesn't work is just as important as knowing what does work. So we have a lot of impact structures on Earth. There are areas where we have a lot, you know, here up here, like near Scandinavia, in the kind of central and eastern United States, Australia, and then we have areas where we don't really have very many, like on the coasts, Africa, etc. Does anybody want to guess why that is? And again, don't be afraid to be wrong. I'm wrong a lot. It's how I learn. I'm going to give you a hint on the next slide. So just be thinking. You don't have to say it out loud. I'm not looking at the chat, but be thinking of why that might be. Because if you see a picture of the Earth, of the moon or Mars, there's craters everywhere, right? So why don't we have craters everywhere on Earth? Which we would expect. Now there are some factors.
Come on, they need to put it in the chat. Come on, I did it. I showed my ignorance. So Mary also wrote it. Come on. Cool.
So
we have several guesses.
Yes, these are all great things. These are all true, you know, to some extent. So, like we don't really know about the bottom of the ocean. So maybe there's a lot of craters. We don't know. There is atmosphere that does protect us, right? So that, I mean, it wasn't always there, but it's there now. And that's a big thing. Another thing, so here's the dinosaur killer, by the way, right here, Chicxulub, in Mexico. One special thing about Earth is that we get new crust. All right, here's where all the volcanoes in the world are. So if you see the ring of fire, here's a bunch of fire in a ring. Look, there's not this one volcano in Australia is, I believe it's dormant. I don't think it's technically extinct, but has not been active for a very long time. Up in Scandinavia, oh, look at this, not many volcanoes. So let's overlay these two together. Well, what do you know? So where we have a lot of volcanoes, we don't have a lot of craters. Where we don't have volcanic activity, we do have impact craters. So that's pretty cool. On Earth, we get new crust in the form of volcanic eruptions, which is really awesome, but it does cover existing craters. That's what happens on Earth. On other planetary bodies, there's a phenomenon called impact gardening. You can impress your friends at parties with this fun fact. So sometimes you have a crater and then you have something else hit it. And so when you get it, when one crater gets hit enough times, it can kind of wear away the evidence that that crater was there. So on other bodies in the solar system, solid bodies, it's mostly impact gardening. But here on Earth, we get new crust. And so our volcanoes, which are great because they are a big part of why we can survive on Earth, they do cover up some of that existing craters. So I just think that's a fun fact. All right, how freaked out should you be about this? Not at all is the short answer. Because we're Los Alamos, we want to relate everything to a bomb. So here's Hiroshima. And you think of Hiroshima as having a lot of energy, of course, but large space impacts have usually more energy than a nuclear weapon. So that's also a fun fact. I mean, not that fun if you're there, but Chelyabinsk right here, this is in 2013. That happens on the order of maybe decades. So that's, we had something in Botswana that was a little less energy, but was also, happens a little more frequently. If your Google clickbait is anything like mine, it's pretty much all impact stuff like craters and asteroids and like the royal family. So that's my fun Google history. And so it always like, ooh, big thing happened and we didn't see it. We're not looking for small things. We're looking for things that are the size of a building. So yeah, the Chelyabinsk thing we didn't see in advance, but we know that's not going to really pose a threat. So we don't look for things that small. So don't be fooled. Be a conscientious consumer of what is out there. Meteor crater in Arizona happens on the order of to 10,000s of years, and that was 50,000 years ago. It is one of the best preserved craters on Earth. Craters in a desert are great because there's not a lot of wind and rain and things that will erode the crater. If you have not been to Meteor Crater and you get on I-40, depending on where you're located, go west or east, and it'll be there. And it's cool. It's open to the public, and it's a really neat place to go. It's a huge crater, and it's really cool to see. It is tiring to walk around the rim, so I brought a chair. I recommend that. Tunguska in Russia is about on the same order of the size of impact of Meteor Crater. Now that was in the late 1800s, which is cool because we actually have recorded history of that. It flattened an entire forest. Yay! So that's neat. Then we have Rees Crater in Germany. I have some shatter cones from that in my office. I forgot to bring them home, but just imagine rock that has a lot of layers in it. Chesapeake Bay is actually an impact structure, but what is not an impact structure is Crater Lake. That is a volcanic crater. And finally, the big one, the dinosaur killer, Chicxulub, 66 million years ago. That happens on the order of every hundreds of millions of years. You can see an equivalent of TNT. This is close to 1 billion megatons, which is a very bad day. So, but you can see the things that happen more frequently are less energy and less of a threat. Things that are a threat happen on the orders of millions of years to even hundreds of millions of years. So don't worry, the odds of this happening in your lifetime are practically zero. So I'm a member of the Double Asteroid Redirection Test team. We impacted in September 26th of 2022. And I just remembered I forgot to include my selfie with Bill Nye, but I did meet Bill Nye at that, and I did take a selfie with him. I took like 3. So I don't know, if you follow me on Twitter, then you'll see that. I can send that out later too if people actually want to see me with Bill Nye. So the goal of this thing was to test in space a kinetic impactor, which is like a space cannonball. So we're going to fly the spacecraft, which is like a little box with wings, and we're going to smack it into an asteroid. Now, it's not very often that you can ask the government for, like hundreds of millions of dollars to crash something, but this time they said yes, which is really awesome. This is the first time we've actually tested this at full scale, which is really exciting, and it worked, which is also really exciting because we weren't going to see the target asteroid Dimorphos on the camera until an hour before impact. And at that point, the world has been watching for months. So that was very exciting when we locked on the target, when we impacted, we all screamed and cheered, and it was amazing. It was a lot of fun to be part of that. All right, so we're using Lagrangian Codes. I will skip over some of the squiggly stuff in the middle here, but basically, in order to do scientific research, the first step is to convince yourself and the scientific community that your method is sound. So we call that validation and verification, which is a lot of what my group does. So we did that with our codes. We looked at different spacecraft geometry effects. We looked at how much momentum gets imparted to the asteroid based on velocity and mass of the spacecraft. Our goal is to change the orbit. It would be a success. I believe 12 seconds was the threshold of a success. We changed the period by more than half an hour, which is great. Very exciting. We're looking at crater dimensions now, and we're working with people all over the world on this mission. I have preliminary results. These are fresh off the press. The rest of the mission team has not seen this yet. You are the first. So when we actually ran into Dimorphos, we noticed it's a whole bunch of stuff stuck together in space. We call that a rubble pile. Now, a rubble pile, but it's not spherical because we don't have wind and water and things that make the rocks smooth like they are here on Earth. They are jaggedy messes. So we have the asteroid shape, and we have the boulders that are on there. Now, I will make these slides available to the team later, but I need to color correct it because I know this is not colorblind friendly, and I apologize for that. I did not have time because, like I said, these are brand new results. I literally just got them yesterday. So it was show you something. I will make the colors prettier, and it's highly oversaturated too. But we have what it looks like here, which is our wonderful asteroid. And a fun fact, when we got to Dimorphos, we compared, one of the mission team members got a bunch of candy, went home with his kids and measured all the different candies to see which candy most represents Dimorphos, and it's actually a peanut butter M&M, or a peanut butter filled chocolate candy coated thing, because M&M is a brand name, right? So that is about the shape of Dimorphos, which is really cool. Let's look at a zoomed in version. All right, so here is a zoomed in version. Now this is actually where we hit. We hit between two boulders. This is our spacecraft. So the spacecraft, if you recall, was a box with wings. That is very hard to simulate. We found in some preliminary studies that doing 3 spheres in a row works just as well and is a lot easier to do in a computer. So part of science is knowing when you are good enough, because you will never be perfect. So 3 spheres in a row is good enough. And so here we see it just about ready to impact, which is really neat. And after it impacts, look at that. It's all shattered, which is what will happen. It's moving very fast, about 6.1 kilometers per second. And that's going to shatter and crash. And you can see we have some boulder reforming already. I'm going to put my mouse here and I'm going to move. So you can see we're already changing the surface. These results, like I said, are brand new, so I don't have much more analysis other than pretty pictures. But that is part of what we're doing here at the lab, is to simulate how this happens, how we smash a spacecraft into an asteroid, what kind of crater we get, and how we change the period, which is very cool. Looking to the future, you can mark yourself safe from the asteroid apocalypse. I have one video I want to show, and I have backup slides if you have additional questions. This video is on asteroid 16 Psyche. It is the largest metallic asteroid in the main belt. It is thought to be part of a planet that did not finish forming and got blown apart. So Earth has a metal core. Psyche is a big hunk of metal in space. This is a 16-second video. It might be the best 16 seconds of your day, so brace yourself, prepare accordingly. So we have our impactor, and we have material flying out of the crater. And
I don't think we see it.
That's very sad. Well, I will email the video to your organizers, and they have my permission to disseminate that to the entire SAGE group if they would like. Because it is a very, okay, well, I apologize. That was not the best 16 seconds of your day.
But they will, as soon as we share it with them.
Yes, but I will send it so you can share it. I think I need to leave time for questions now. Is that correct?
I think we've got time if you've got more you want to say, but we could also go to questions.
Okay. Acknowledgements, obligatory. Yay, people gave us money. I will leave this up so people can screenshot if you would like. That is my email. That is my work. That is my work cell phone. I do screen, so please text first, because if I don't, but generally the work cell phone, I will answer all the time. So if you have questions that you think of later and you want to ask them, you are welcome to email me or call me. That's totally fine, or text me. And some background on Psyche. I will, once I color correct, I will send these slides as well, so you can have access to it. Some pretty pictures from the video. So there's a pretty picture. Creator profiles, some cool stuff. I didn't want to put too much and just overdo it, but there's a lot of kind of squiggly stuff in the middle, technical stuff, but I did want to highlight that, you know, what we're doing for planetary defense is a really interesting problem. And all of my degrees are in math. So I have had one physics class in my entire life, and it was graduate level biophysics. And it was very hard. I don't recommend that as your first physics class, but I learned a lot at work, and that's what I do mostly. In practice, I do computational physics every day. I am a trained mathematician. That's what all my degrees are in, and I do love math very much. And I always did. I actually have math trophies, which is a thing that happens. And yeah, I am happy to take any questions you have on my research or on my career path, or I don't know, if you want to ask about my cat, I guess you could do that too. Like I said, I will make the slides available after I color correct them, because I always try to be mindful of that, and I will make the colors better, I promise. And if I get some more analysis, I'll throw that in there too. But you are the first people to see those images from those simulations. So that is pretty cool. I haven't even shared them with the mission team yet. So thank you for listening. I'm happy to take your questions. I will leave the slide up with my contact information, so you can write that down if you would like. If you have a question you would rather ask, you know, not in a group setting or something, that's totally fine. I will turn it over to the moderators now to field questions.
Yeah, thank you very much for an excellent talk. We've got a question in the chat. Do you have any advice for learners who love math but have learning disabilities and math phobia?
Yes. So one thing I try very hard to fight the math phobia, because that is a thing. And it's interesting. Math is the only thing I know of that when I tell people I do it for a living, everybody is excited to tell me how bad they are at it or how much they hate it. So it's not like somebody says, I'm a truck driver, and everyone's like, oh, I'm a terrible driver, right? That doesn't happen. But with math, it does. One of the things is to use your resources. So pretty much any university and school will have a way to get an accommodation. So I have had students in the past who have accommodations where they get extra time on tests, for instance, or extended time to turn in assignments related to any type of disability. And I will also add that, especially at the college level, you do not have to tell your instructor what that is, right? That is confidential information. Your university will probably have a disability resource center or something along those lines where you provide documentation and they work with you, and all they do is tell your instructor, this person has an accommodation and here's what it is. So I've had students who have had those in my classes, and they've been able to take tests sometimes in a different location where they have more time, or have extended deadlines on assignments and things. I think that's really great that we do. I personally had disability accommodations when I took my comprehensive exams because I had a severe concussion and I had to have extra time because I was on brain rest for a long time. As far as math phobia goes, one of the best things is to not be afraid to be wrong. And that's very hard. It is very hard. I get that. The more you get in your education, the less afraid you are of being wrong. You don't have to understand everything the first time you try it. I wish somebody had told me that earlier. I hated PDEs when I first did them. That's partial differential equations. It made me cry a lot. And now I do that all day, every day, because I've gotten better at it. So there are things you don't understand yet. It doesn't mean you can't understand them. And if you're used to getting things right the first time, it is very hard to then come across something that you don't get right the first time. That's very difficult. But it's okay and it's normal, especially at the graduate level. You can get a 30% and that's a B sometimes, right? Because the stuff is so hard. So I encourage you to explore. There are some great information online. Paul's online notes, I think is what it's called, has really great breakdowns of college level mathematics, and which are probably taught in high school as well. So if you look Paul's online math notes, if you just Google that, great resource. Great YouTube references too. There's a lot of great YouTubers who actually do mathematics content and break it down in an easier way. If you're into probability theory, my husband has a YouTube channel on that. I've done enough of that to get a math degree, which is not much. But it is a real thing. And I encourage you to embrace the fact that sometimes things are hard and that's okay. And you don't have to get it right the first time. And that's also okay. And if you don't I tell my students when I was teaching in grad school, if you learn it for the final exam, that's the goal. The goal is to learn it by the end of the class. And if you learn half of it and have to take the class again, well, that's great. You've already learned half of the material. Now you have an advantage. So there's no shame in that. There's no shame in needing to do something more than once, or to, I had to take one of my qual classes again, and I was worried about it. And one of my professors was like, nobody cares, Wendy. Like, nobody even knows unless you tell them. And it's because I injured myself pretty severely a week before finals and couldn't study. And so I just bombed all my finals, and which happens, right? Life gets in the way. But the important thing is to keep going, right? Just keep swimming. And
Just keep
it's
swimming,
okay.
Yeah. We have more
Yeah, just keep
questions,
swimming.
Wendy.
Oh,
Let's see,
then yes.
Andrea.
Sorry, I talk a lot. I'm an extrovert. Keep going.
No worries. Yeah, I know I had to drop my quantum mechanics class in undergrad because I bombed the midterm. And so I took it again the next year and then managed to do better. So yeah, sometimes it's just, you just stumble and you got to get back up. Okay, so we've got a question. A lot of girls drop math and science in high school and may start in college, but then drop as well. And your journey shows us that it's possible to persevere. Is there any words of encouragement that you have for young girls considering a future in math and science?
Yes. So for one thing, math is not a gendered thing, despite what popular culture tells you, right? Women are just as good at math as men. And I don't like phrasing it that way, because a man's level of accomplishment should not be your benchmark for what is great, right? The goal is to learn more than you learned the day before. And if you do that, you succeed. There are people who will be maybe threatened or uncomfortable by your success. That is the problem for them. That is a them problem, not a you problem, right? So I have dealt with some gender bias throughout my career. Success is the best revenge, I have found. I mean, they don't have selfies with Bill Nye, and I think
I found your selfie. I found your selfie, Wendy, and I'm trying to figure out how to share it, but I'm stumbling with Facebook challenges here.
I guess you could share your screen at some point, but it is important to know that you believing in yourself, or a really great instructor believing in you, is enough to get you through that usually. And don't listen to the people who tell you can't do stuff. So on the back of my neck, I have an infinity tattoo, and that's to remind me not to place limitations on my abilities. So it can be hard, but then it's also incredibly rewarding to, like I said, I was the only girl in my graduating class to get a math degree and to get a math award. Now, I didn't take calculus in high school. I took extra theater and I still have a PhD. Live your life too. Don't burn yourself out. You are not representative in math. That is important to know.
Yeah, that's a really good
You're
point.
representative of you.
So do you have any advice for someone who wants to work for NASA?
Oh, yes. So email me for one thing, and I can put you in contact with some people. Depending on what you want to do. So they don't pay me. I get paid by the lab, but I am on the mission team. But they do have special, if you look up NASA Roses, ROSES, they have special calls for proposals and things. So at the college level, you can certainly get involved that way. They often will have a, executive secretary when we review proposals, who is a person who does takes notes when we review proposals, so you get some exposure. There is a conference coming up in March called LPSC. That's Lunar Planetary Science Conference. It is in Texas, but it's hybrid. There's a virtual option. A lot of times conferences like that, the same thing with American Geophysical Union, which is every December, they will have very discounted rates for high school students to participate. And NASA is there every time. They have a NASA night. It's usually Monday. That's when we're doing our DART mission stuff. So if you follow NASA on Twitter, they also announce those kinds of things. And STEM is a great way to go to be involved in NASA, a STEM degree. And then don't be afraid to just email somebody and say, hey, I'm interested in what you're doing. Would you talk to me about your research or about your career? Nobody has ever told me no. People love to feel valued and they love to talk about their work, especially if they're passionate about it. And when you reach out and you say, hey, I'm interested in a career with NASA in the future. I'm now in X year of school, high school or college. What should I do? What can I do? The goal of going to school is to eventually get a job. So think of the career you want, look up what it takes to get that career, and then start planning ahead. If NASA requires you to have a degree in, STEM, then plan to declare a major in STEM. If to get into that program, you need to take X number of math and science credits in high school, go ahead and start planning that now. Your guidance counselor at school will be an excellent resource, and the Career Center at college will be also an excellent resource. But don't be afraid to just look up, NASA career fair, stuff like that. You'll find information. At minimum, you'll find a contact person that you can reach out to and ask for more information.
Yeah, awesome.
I also
And
posted that NASA summer internships are now open. If you go to the website I put in the chat, you can apply for an internship, and you will see that there are different levels of internships for the summer for high schoolers and undergrads.
that's a great resource. Yeah, thanks, Anna, for posting that. And I think that, Wendy talked about a whole bunch of different resources. And so, if you had further questions or you didn't catch all of it, please email her and she can tell you more.
Or come to Matilda tonight.
Yeah, there you go. You can meet her in person. She'll be the one with the pink hair and the jewels on
I'll be the one with the gems on my face. Well, actually, not just me.
All right. Do you have any advice for battling imposter syndrome?
I think we
I think
lost
Comcast
Wendy. Yeah, Comcast play a trick with us.
Okay, well, I guess I suggest that we whatchamacallit, that maybe we move on to Dan, and then we can come back and have questions for both of them after Dan's talk.
Yes, I think that's a fantastic idea.
Okay, great. Let's do that. So let's put a pin in it and we'll come back to your questions in just a little bit. Okay. Now we're going to hear from Dan Reisenfeld. Dan has been a senior scientist in the Space Science and Applications Group at Los Alamos National Lab since 2018. For the 14 years prior to that, he was a professor of physics and astronomy at the University of Montana. And before that, he was a scientist at Los Alamos. So he left and he came back because Los Alamos is so awesome. Dan,
we call that a boomerang career.
Boomerang career, yeah. Dan has broad space science interests, exploring questions such as how does the solar wind get accelerated to millions of miles per hour, and what secrets do the outer planets hold? What forms and controls the interstellar boundary between our solar system and the rest of the galaxy? Over his career, he's been involved in a number of NASA missions. He was a team member for the Cassini Plasma Spectrometer, or the CAPS, aboard the Cassini mission to Saturn, and a deputy instrument lead on the Interstellar Boundary Explorer, IBEX. Dan is now leading the development of the IMAP High instrument for a new NASA mission. That's the Interstellar Mapping and Acceleration Probe. And it's expected to launch in 2025. A native of Cincinnati, Ohio, Dan received his PhD in astronomy from Harvard and a bachelor's in physics from Yale. And so we're going to hear about some cool NASA missions. So Dan, take it away.
All right, thanks. And hello, everyone. It's nice to be here, and this is a great way to spend a Saturday morning. So I, too, could happy to answer the questions that you had posted for Wendy. I have my own addition, some thoughts on those things as well. But first, I wanted to tell you a bit about the kind of exciting, science that a person can be involved with working on a NASA project. One of the things I wanted to mention is that, the question was asked, how do you, get a job at NASA? And a lot of the scientists who are NASA scientists do not work at NASA. In fact, Wendy and I are perfect examples. And there are people who work on NASA missions scattered throughout academia at different colleges and universities around the country, as well as at different laboratories. NASA funds research all over the country. And so you don't literally have to have a paycheck from a NASA center in order to be involved in any of the stuff that I'm going to be talking about and that Wendy was talking about. So let me start sharing my screen here. Hang on a second. Okay, hopefully I am sharing my screen. And should now be in slide.
Yes, we can see it.
Mode. Okay, cool. All right, so you heard in my bio that Andrea gave that I'm involved in lots of different things. One of the favorite parts of my career was working on the Cassini mission to Saturn. And I wanted to talk about that because of the various things I work on. This is one of the more approachable ones for people who aren't my colleagues. So it's a good one to start with. So I'm going to be telling you a bit about the Cassini mission to Saturn, as well as some of the things we learned when we went to Saturn. And then I'm going to be talking about the team and the kinds of careers that are involved in space missions like the Cassini mission. And I too have a bio section that I will add at the end, and I'll end with that before going on to questions. Okay, so the full name of the mission, the Cassini mission, was the Cassini-Huygens mission. The Huygens probe was built by the European Space Agency, and I'll get to that in a minute. But basically, the background of this mission was that back in the early 80s, NASA launched two probes called the Voyager probes, and they flew out and did this grand tour of the planets. Some of the first photographs we ever got from the outer planets came from the Voyagers in the early 1980s, and they found many more questions than they answered. So this is a picture from Voyager of Saturn taken by Voyager in like 1981. So in 1990, NASA and the European Space Agency decided to build the Cassini-Huygens mission as a focus mission just to Saturn. The idea was to actually go in orbit around Saturn and spend a long time there. And it ended up, they spent 13 years orbiting Saturn. So it was launched in 1997. Some of the instruments on the Cassini spacecraft were built here at Los Alamos. Again, they were built, the instruments on Cassini were built on lots of different places. It was launched in 97, and the goal of the mission is to study Saturn, Titan, Saturn's rings, and its other moons, and how all of these things interact with one another too. And you'll get a sense of what I mean by that in a minute. The Cassini team is made up of over 270 scientists from around the world. And even though the mission ended in 2017, we're still analyzing data. I have a grant right now, in fact, to continue to analyze data from the Cassini mission. I realize that I am talking to a number of young women, and so I want to emphasize how there are leadership roles in our field for women. For example, this is the Cassini project scientist, Linda Spilker. She's our boss and during this mission. Of these 270 people around the world, she basically was the one that kind of told us what to do. All right, the Cassini spacecraft, as I said, it was launched in 1997. It took 7 years to get to Saturn, arriving there in 2004. And it finished its mission, as I said, for me, it doesn't seem that long ago, 2017, maybe for some of you guys, that seems like you were just, starting school or something like that back then. But for me, that was just like yesterday. So 13 years it was in orbit around Saturn. And so the Cassini spacecraft was huge. I mean, it was literally the size of a school bus. Here is another picture of the spacecraft, or an illustration showing all of the scientific instruments on the, let's see, let me get the pen here. There we go. So you can see the different instruments, a magnetometer, which is a kind of thing that measures magnetic fields, radio and plasma wave antennas. Remote sensing is a fancy word for cameras. So that's all the cameras that took pictures over here. I was working on one of the instruments on the fields and particles palette, specifically that guy right there, which was the ion mass spectrometer. And it basically, as it flew through the space around Saturn, it collected plasma that is floating around the Saturnian environment and determined its composition. What was that plasma made of? And I'll get to that in a minute as well. All right, so as I said, it took 7 years for Cassini to get to Saturn. And in order to do that, it turns out that there's not, at least in 1997, there was not a rocket powerful enough to directly fly to Saturn in a reasonable amount of time. So what the mission designers did was they used gravitational assists by slingshotting the spacecraft past other planets to pick up speed, basically using the gravitational energy of other planets and to accelerate the spacecraft. So here in 1997, the Cassini was launched. It flew by Venus. It actually went in towards the sun, flying by Venus in 1998. It then flew in this red arc for another year, and then it flew by Venus in 1999. And each time it flew by a planet, it got a velocity kick. It started going a bit faster. And you have to, for every action, there's an equal and opposite reaction. So that means that the planet itself that it flew by had to slow down a tiny, tiny bit to impart some of its momentum to the spacecraft. So then it flew by the Earth again, came all the way back to Earth in 1999, used Earth's gravity to kick it again, and then it had a long cruise, flew by Jupiter in 2000, got another really big kick, and then it was going fast enough to make it out to Saturn in 4 more years. Okay, so here it comes streaking into Saturn's environment in 2004, and it was going so fast that it actually had to use Saturn to break the speed of the spacecraft to trap it into an orbit around the planet. And to slow down enough, it had to get close enough to Saturn to bleed off enough of this speed, and it had to fly between that gap between the innermost edge of the inner ring and the outermost part of Saturn's atmosphere. So it had to literally thread this needle. This was terrifying for us on the mission. This is equivalent to, so I'm here in Los Alamos, Albuquerque is about 100 miles away. Imagine someone hold a quarter up in the air in Albuquerque, and I'm standing here in Los Alamos on a mountain, and I see that quarter. Well, maybe I can see that quarter, and I aim my rifle to shoot that quarter that someone's holding up in Albuquerque. That is the equivalent to how accurately the navigators had to plot this trajectory in order to successfully make it through this tiny gap here between the moon, between Saturn and the rings. So this was breathless. We were only in contact with the spacecraft during the green parts here. That's when the big antenna on the spacecraft was pointed towards Earth, because the spacecraft had to repoint to also fire its retro rocket to slow down in order to help bleed off some of its speed. And so in this white part and red part, we had no contact with it until it came out over here. So on June 30th, we intentionally were out of contact. And then a couple hours later, on July 1st, we regained contact and everybody breathed a huge sigh of relief. And then we started to get our first images of Saturn from the Cassini spacecraft. And so this is an image of Saturn, one of the first ones taken by Cassini. And you can see this, I could blow this up. I mean, this would be great, backdrop on your screen. I mean, it's a really high resolution, gorgeous image. One of my favorite images of Saturn taken by Cassini is this one. It looks kind of odd because what is going on in this picture is Saturn itself is blocking out the sun. So Cassini is in the shadow of Saturn, looking back at Saturn and its rings. And so the rings are scattering sunlight. And so you're seeing scattered sunlight through the rings. And there's enough scatter that you can even see scattered light on the rings behind Saturn here. And it also highlights some interesting things, like, for example, there's this halo-y like ring that you don't see easily from Earth, which is called the E ring. I'll talk about it in a minute. Turns out this ring is made, well, all of these things are made out of, well, actually, I'll ask you, what are Saturn's rings made out of? Any guesses? Let's see, I have my chat up, so I see dust, ice and rock. Ice, yes, ice is the right answer. So Saturn's rings are basically blocks of ice. This particular outermost ring here is water vapor. So that's an intriguing thing to see, because this water vapor is curiously being bound there, but why is it there? I mean, we know now, but we didn't then. Okay. Another interesting thing about this photograph is that this proves that we went there, because you can't take this picture from Earth. Why not? That's another question, if you want to put it. Why can't you take a picture like this from Earth? Like in a telescope of Saturn. I mean, we have some really good telescopes on Earth and we can take pictures of Saturn easily. Why can't you take this particular picture? Saturn is in between. Yes, that's right. So obviously Saturn has to be between the camera and the sun. And since Earth's orbit is interior to Saturn's orbit, there's no way that you could take a picture of the backside of Saturn from the Earth. Good job. All right. All right, so moving on, I want to tell you a few facts about Saturn, and then I'll get into a story about one of the most exciting things that was part of my experience studying the Saturn environment. So Saturn is really big. It's 60,000 kilometers across, which is about 10 times the diameter or the radius of the Earth. It has a rotational period of about 10 hours, and it's about 10 AU from the sun. And AU is a convenient unit of measure we use in the solar system, where 1 AU is the distance from the sun to the Earth. So this is 10 times further away from the Earth than the sun is. So lots of tens here, 10 times the diameter, rotational period 10 hours, distance from the sun, 10 AU. It has a lot of moons, 62 major moons, and then, almost an infinite number if you start counting all of the little ice particles and such. The atmosphere of the planet itself is mostly hydrogen, 97%, 3% helium, and trace amounts of methane and ammonia. And only at the very core is there sort of a rocky center that we would think of as like a planet in the sense of an Earth-like planet. There's a rocky core, which actually is about the size of the Earth. Otherwise, everything you see here is gas. It has a very strong magnetic field, about 600 times that of the Earth. And it also has a moon, and you actually see a picture of it right there. That moon there is Titan. And Titan is the second largest moon in the solar system. It's actually larger than the planet Mercury. And that's what the Huygens probe was put on the Cassini mission for, because it was there to land on the surface of Titan. Titan has a dense nitrogen atmosphere, and it's very similar to what Earth was like before life formed. The reason life has not formed on Titan is because it's very cold there. And so it's basically a frozen Earth. But it does actually have lots of organic molecules. In fact, it even rains methane as a liquid on underneath the clouds of Titan. So more of that in a minute. All right, well, as I said, Saturn has many moons. And so the Cassini mission intended to fly by lots of those moons over the course of the 13 years it was there. And this animation is showing you the trajectory of the Cassini spacecraft over time. By the time this movie ends, about 13 years will have passed. Each one of these orbits is a couple of months long. So you can see that it changed the inclination of the orbit over time. And some orbits were further out, some were further in. The white circle is the orbit of Titan. And in fact, it used Titan as the white circle is Iapetus. Closer in is Titan, and it used Titan as flybys of Titan to change its orbit so that it could tilt the inclination plane to different degrees by close flybys of Titan itself. So there you go. So I'm going to tell you a story about the moon Enceladus. Before the mission, Enceladus was a fairly nondescript moon, a cold, icy moon of Saturn. But we discovered that it has an atmosphere. And the way we discovered that it has an atmosphere would be surprising. At least it was surprising to us. It actually was discovered by the magnetometer team. Remember, I told you that one of the instruments there was like an instrument out on a boom, and that's the magnetometer. It measures magnetic fields. The magnetometer team is led by Michelle Doherty. She's at the University College London. They discovered that the magnetic field of Saturn was deflected as Cassini flew by Enceladus. And the only way you can deflect a magnetic field from something like a planet is if you have ions in that environment. And the only way you can have ions there is if you have an ionized atmosphere. So by deduction, they figured this out. So here's the kind of picture. So Cassini flew by Enceladus, and these purple lines tell you the direction of the magnetic field. And they noticed this deflection in Saturn's magnetic field, which was a hint that there must be something going on at Enceladus. So this is what the actual data looks like. I won't get into it, but basically these little lines here, the long lines are the trajectories of the spacecraft going by Enceladus. That's the circle. And the short stubby lines are indicate the strength and direction of the magnetic field, showing how the magnetic field got deflected as we flew by and Enceladus. Okay, so what was the source of this atmosphere? Well, here's a picture of Enceladus, and you notice at the south part of the moon, there's this bluish, what looks like cracks. We thought maybe something was coming out of the cracks. And so if you look in closer at those cracks, we asked the navigators to direct Cassini closer to Enceladus than originally planned. And we got this close-up view seeing these fissures in the ice. So what you're basically looking at is an ice field with these bluish crevasses or ice cracks, ice canyons in them. And basically we learned that Enceladus is erupting geysers of liquid water. This is data from my instrument, the instrument I worked on, which was the ion mass spectrometer. But basically, I'm not going to explain what's going on here, but in these little squiggly things here were observations of a cold water source as the spacecraft flew right by the south pole of Enceladus, in the shown over in this plot here. And then on the next flyby, we went even closer, and we were able to take images showing water geysers shooting off into space. You can actually kind of make out the crack there, and you can see the plumes of water coming out. And here's another picture of Enceladus from further away, showing the water plumes shooting out of the South Pole. And that explains the E-ring. This ring of water vapor here is because this is the orbit of Enceladus. And in fact, right there, you can see a little dot, that's Enceladus. And so Enceladus is filling Saturn's space with water vapor continuously from these jets. Now, this is cool, but what's really exciting about that is the implication. If you have water jets shooting out into space, that implies that underneath the ice is an ocean. There's literally an ocean of liquid water underneath the ice of Enceladus. And obviously, since it's liquid, it means it's warm enough to support life. And in fact, we now know from other observations that there are enough organic molecules in that water, and there's enough heat in that water that it's feasible that life could form or has already formed underneath the icy crust of Enceladus. So there you have it. All right, so I'm going to finish talking about Saturn by looking at some pretty pictures that Cassini took while it was there. Here you can see a storm on the surface of the in the atmosphere of Saturn. The storm basically formed here and caused kind of like, because Saturn spins so fast, there's sort of a turbulent wake from the storm that actually wrapped around on itself. You can see it here. This storm appeared and disappeared over the course of about 10 months. So that was something we did not know that happened on Saturn before then. You may have heard of the Jupiter's big giant red spot. This is kind of like Saturn's answer to that. At the pole of Saturn, there's this weird hexagon in the clouds. That was a surprise, and we're still not entirely sure what forms this hexagon shape. But if you look in even closer, there's this interesting little blue circle here. If we zoom in really close there, that's what's in the middle of the blue circle. That is a super close up of basically the polar vortex at the pole of Saturn. So this goes right down into the North Pole. You can see storm clouds, there's lightning. It's like a science fiction movie. I mean, it's like just, it's just happening right now. It's incredible. All right. This is a moon in one of the rings. It turns out that the rings of Saturn are stabilized by little tiny moons that we call shepherding moons. And these moons basically, because of gravitational attraction, they keep in line all of the ice particles in the rings. Otherwise, the rings would dissipate in a few thousand years. But thanks to these little moons that Cassini discovered, we now understand why the rings are stable. Here's another moon. This moon is called Hyperion, and it is mostly empty. It looks like a sponge because it literally is a sponge. It's mostly voids with rocky material, but there's a lot of emptiness there. Still trying to figure out how that formed. This one is the moon Mimas. We nicknamed it the Death Star because of the planet killer radio dish that's obviously there on the side of it. That's just a crater from an impact. It's nothing that exciting it's not that mysterious. It just is a curious looking thing. And here is Titan. As I had mentioned, Titan has a very dense atmosphere, so dense that with visible light, you cannot see the surface of Titan. But if you look at it using infrared light, you actually can see underneath the cloud's surface. And if you use radio waves, you can even more carefully map out that surface. And here is using radar to probe down below the surface. This is a lake of methane underneath the clouds on Titan. So this is an ocean. You can actually see rivers and erosion from methane waterways on Titan. Titan is such an interesting place because it is where it has all the ingredients for life. It has organic molecules, it has lightning, it has liquids. We don't think there's any life there because it's too cold, but just the chemistry of the place is enough to warrant more inspection. This is another beautiful shot. This is the ring here of Saturn. That's Enceladus, just caught apparently hovering over the ring. You can actually see shadows of the rings on the surface of Saturn here. So the sun was, kind of below, sunlight was coming in from the lower left, shining up through the ring, edge on, and casting the shadow of the rings. So the Cassini mission ended in 2017. We intentionally ditched the spacecraft into the atmosphere of Saturn. And here is an artist's illustration of what that would have looked like as Cassini basically broke up as it flew into Saturn's atmosphere. This is not a photograph. I mean, there was not another spacecraft there to take this picture. This is a painting. But I can show you the last set of images that Cassini took. We pointed the cameras at Enceladus because Enceladus kind of was the star of the show for the mission. And as the spacecraft plummeted into the clouds, these were the last images that it took before Cassini was lost. Right there. And that was the end of the mission. All right, so here is that team. I don't think all 270 people are in this picture, but there's an awful lot of people in this picture. We gathered at the Jet Propulsion Laboratory in September of 2017 to watch the last transmissions from Cassini. That's me amongst all these people here. Lots of people, young, old, men, women, from all over the world came to gather at JPL for this. But the mission's not over to Saturn. Well, Cassini isn't over. We're getting ready to fly another mission there. In 2027, we're launching a mission to Saturn called Dragonfly. It will get there 7 years later, 2034. And it will be going to Titan, and it will actually have not a rover, but a helicopter. And here it is. This is, we call this Dragonfly. It's an 8-bladed helicopter. Fly down to the surface of Titan. Because again, Titan has an atmosphere. That means you can fly in it. Mars doesn't have enough atmosphere to really fly in. These rovers on Mars. Titan can fly around. It lands, collect data, they take off again, and fly somewhere else. Land again, and hop around. As you can see I'm wearing my Dragonfly t-shirt here because I think this is a really awesome, cool mission. And if you notice the dates, this mission will be happening in, it hasn't even begun yet. There's still time to get involved in this mission. I mean, it's being built right now, but, it'll launch. By the time it launches, maybe you'll have an opportunity to be a scientist or one of the controllers or somebody that's involved in this mission. Another thing I like about the Dragonfly mission is this plot, which shows you the number of women on NASA science teams as a function of time. And you can see starting back with the Vikings way back with the first missions to Mars back in the 70s, no women. Even Cassini didn't have a lot of women. Only 3% of the science team, at least in 1992, was female. And but now Dragonfly here, we've reached near parity, where half of the science team are women, or nearly half. And that is quite a triumph. And you can see the trend over time. So there are opportunities for anybody now. And the doors are wide open. So, and in terms of what kinds of jobs are needed to run a NASA mission, here's a list. I mean, you don't have to have a PhD to be participant in a NASA mission or to run a NASA mission. So I'm listing various things here. Of course, there's scientists, PhDs. That probably means 4 years of college, and now there are 4 to 6 years of graduate school. And yeah, space scientists, planetary scientists. You don't even need to be, there's also laboratory scientists, people who just like working in laboratories to build the instruments and test them. Postdocs are people right out of graduate school, their first job after graduate school. There's also lots of students involved. As I said, you do not have to go work at NASA to be involved in a NASA mission. There are universities all over the country that have graduate students and undergraduates even working on these projects. Postbacs, I have a postbac here at Los Alamos working on the IMAP mission with me. That he's between undergrad and grad school. Also, I heard the question about STEAM. So there are a huge need for educators and public outreach specialists. Every NASA mission also has a group whose their job is basically to communicate the excitement of the mission to the public. They're employed by NASA or by other organizations that partner with NASA. Artists and illustrators. I mean, I showed you pictures, paintings of Cassini. I mean, that was by somebody that worked at NASA. Science writers to write the press releases and things from the various missions are employed by NASA and by institutions like Los Alamos and such. Of course, we need lots of engineers. That's just a master's degree. You don't need a PhD in engineering, just a master's degree. Systems engineers, mechanical engineers, electrical engineers, thermal engineers, structural engineers, the list goes on. You just get one of these degrees and then you just look around and see if you can find a job at a place like Los Alamos or Caltech or NASA, Johnson Space Center, and they'll put you on these projects. Technologists, people who basically have undergraduate degrees or even associate's degrees, just 2 years of college, to work on fabrication, assembly, and test technicians, drafts people who, make the drawings that the engineers, design something, but then you have to create the drawings that get sent out to the shops to get stuff built. We employ MBAs, people with business degrees as managers, as budget analysts, schedule specialists. It takes, there's lots of ways to get involved in these things. All right, let's see. I've been talking before. All right, so just the last thing I have is just a little bit more about me, and then if there's time for questions, we'll do that. So I was born and raised in Cincinnati, Ohio. My dad was a drywall contractor. My mom was a nurse, so I didn't, I wasn't born with a silver spoon in my mouth by any means. My inspirations were James T. Kirk and Carl Sagan, who was so one is a fictional explorer and one is a real explorer. Carl Sagan was the creator of the TV show Cosmos. That was really big in the 80s, and they even remade it in the last decade by Neil deGrasse Tyson. I didn't always know I wanted to work in space. At some point, I wanted to be an architect. But I realized that the kinds of things I wanted to design looked more like that instead. I was involved in acting. It seems to be a theme today. In high school, I was in Guys and Dolls and Flowers for Algernon. And in fact, that made me want to become a filmmaker. And of course, at some point, I wanted to be an astronaut, but that was more just because who doesn't want to become an astronaut? So by the way, if you do want to become an astronaut, there's 2 ways to do it. You can become a Navy pilot. That wasn't going to happen to me. Or you get a PhD in something like physics or astronomy, which I saw was more something I could probably do. I took a lot of AP classes, physics, math, chemistry. You have to take a lot of math. It's good if you're good at it, but even if you're not, you still have to take it. And that's just the way it is. I actually went to college at Yale as a film studies major, and I realized that, and the reason was because I wanted to be a documentary, science documentaries. I wanted to make Nova or nature type shows, but I decided the arty crowd wasn't a good fit for me, and I felt much more at home with the geeks over in the science department, so I became a physics major. And ultimately, I decided I wanted to build instruments and explore the solar system with them. So these days, I'm building this. This is the IMAP High instrument. This is a rendering. It's not an actual photograph. And this is what it looks like inside, cut away. These are the toys we get to build to study the solar system. So, all right, and that takes care of it. Thank you for your attention.
All right, awesome. Thank you for an excellent talk. I think we have time for a couple of questions. There were some in the chat, so I'm going to do those. So you had a picture with the shepherding moon, and so it looked like the rings were in a straight line. Is that because of the shepherding moons?
It was just because it's very close up. So the shepherding moon picture is that one. So this is a very high zoom in on the rings. So you can see these structures in the rings here. And then this is actually sort of a wave, a little gravity wave created by the moon as it's orbiting around in this lane between the rings.
That's awesome. Okay, so another question is, and you spoke a little bit to this, maybe you can give some more details. How can our campers get involved with Dragonfly right now?
So right now is not terribly easy. I mean, you can go to the NASA websites and learn about Dragonfly. If you just type Dragonfly and NASA, you'll find out lots of information. It's currently being built at the Applied Physics Laboratory, which is in Maryland. Coincidentally, APL, the Applied Physics Laboratory, also built DART that Wendy was talking about. Anyway, they're not NASA, but they are funded by NASA to build spacecraft and instruments for those spacecraft. And so they hire all the time. I mean, you can get it, certainly one can get a job over at APL. But as just being in the environment right now, you'll probably have to wait until 2027 when it's actually launched. And then once it's launched, there will be opportunities to learn about the mission. If you go to, find universities that have scientists that are involved in planetary science and get involved in those groups, and they'll be doing research on the data from Dragonfly or other planetary missions. And that's how people get in the door, is at the universities. Like, University of Arizona, for example, has a big planetary science program. Caltech has a big program. University of Michigan. There's lots of universities around the country that have planetary science or other space science programs, and they have researchers there that are working on it, and they pay graduates and undergraduates to work on their projects.
There was a question for Wendy earlier about imposter syndrome, and I don't know if it was answered, but Dan, I think you said that you had some answers of questions that were posed to Wendy, and maybe now both of you could tag team on that. Do you recall the question about the imposter syndrome?
I do, and I totally am a victim of imposter syndrome today. Even, I mean, it haunts one throughout their career, I think, if you have a soul, it is I'm always questioning, am I good enough to be doing this? I mean, I look around at my peers and I think to myself, I mean, like I said, my dad was a drywaller, right? I mean, it's like, why do I get to do this? And they're going to find out, right? They're going to know. Finally somebody's going to figure out that I really don't know what I'm talking about, and that I don't belong here. And I can only say that you're not alone. That might be the best way to deal with it, is to know that probably 80% of the people you're working with also have imposter syndrome.
So I went to a review, Department of Energy review on Thursday and Friday, and I met one of my colleagues there that asked me, "What are you doing here?" Guess what? My imposter syndrome flag went on.
Right, exactly. Yep.
Like, well, I hope I'm not wasting taxpayers' money by being a reviewer. I guess I'm good enough that they asked me to be a reviewer. But that voice in your head telling you, oh my God, they're figuring out, just went on.
Yep.
For me, I think that the best thing, and I put this in the chat, but it's very hard, but don't compare yourself to anybody but your past self. So if you know more today than you did yesterday, then you're not an imposter. Yay. So it's really hard to do that in practice. But a lot of people have imposter syndrome. Most people do. It's just a matter of a lot of people don't talk about it, and women statistically are more likely to talk about it. But if you focus on your abilities and your talent and your progression through your education or career, and that's what you focus on, it's how you really turn that off. Is, do I know more than I did yesterday? Am I a better scientist than I was yesterday? And if that's the case and you're moving forward, then you're not an imposter.
Awesome. Great advice. I think that we are out of time. So I'm gonna, I guess, hand it back over to Daniela. I guess also just thank you everyone for joining. We will do this again in March, and check out, or look in your email for details when it gets to be closer than that, sorry. And yeah, I guess thanks again. Both Wendy and Dan gave their contact information if you missed it. feel free to email your Sage contact, and we'll get you that information.
And I have the picture of Wendy with
Oh yeah.
Bill Nye. Let's see if I can.
Yeah.
Here you go. Let's see if I can share it. Do you see it?
There I am. He had a space bow tie.
What a fun
Yeah.
picture.
Wendy with Bill Nye, the science guy.
And that was at APL, so we brought it around.
Yep, there you go.
So also remember, now is the time to apply for internships. And I believe that both Wendy and Dan will concur with me on the importance of finding a mentor that often can help you find your way around all these labs. I mean, Dan through MIT, Michigan University. Sometimes a mentor is the key to define the field in which you're going to end up, because they inspire you. So you're a high schooler in California, Tennessee, New Mexico. If you apply for an internship, let your Sage team know that you're applying for it. If you're a New Mexico student applying in California, let us know, and we will reach out to our California folks to help you find an amazing mentor. And also, because you're part of the Sage family, right? For the part of the Sage journey, we have resources to help you find those internships, secure them, and find you a mentor. So I think internships are very often key to understand this complex, path. You don't need to be an astrophysicist to be at NASA in a NASA mission, as we saw from Dan. You can be an engineer, but getting there very often relies on getting into these teams and so on. So now is the time. I believe for Los Alamos, the deadline to put forward, student packages is approaching. So reach out to your Sage team if you're interested in internships.
Yeah, great. Thanks, Anna. Yeah, now is the time. So give it some thought. All right. Well, I guess that wraps up for this month's Sage Live. Thank you again for attending. Thank you to our speakers, and we'll see you in March.
Thank you so much, everyone.
Hi,
Thank you.
thank you.
Bye. Thanks, everybody. Have a good weekend.
Thank you.
Maybe see you tonight, Dan,
That's right.
at the show.